Hello everyone. So this is the why behind what, in which we are going to discuss the JEE Advanced problem, as the series has this theme. And this time I have taken this question from JEE Advanced 2018 paper 1. The question is based on the Lagrange's mean value theorem. So there is another version of the solution you can find on the internet or any other recommended books also, that we assume the function as the trigonometric function sine 85x and all those things. So first of all, read the question carefully. The question says that for every twice differentiable function, which is from r2 minus 2 to 2, with f0 squared plus f dash 0 square is 85. So we have to find out which of the following statement are true. So more than one correct can be possible. So here, one of the idea is that can we identify a function which has this property, like f0 square and f dash 0 square is 85. It's very difficult to identify, and you can find some many solutions in which the function fx has been taken as sine of, I think, 85x or 85 sine x, I think. Because when you take the square and of course derivative at 0 will give you the cos 0 or 1, and from there we can get 85. And it's also valid for all real number, because if you take the sine 85x, this is valid for all real number, the domain, and this is in the minus 2 to 2, so we have to take something in a such a way that the function has the upper bound positive 2 and the lower bound is minus 2. But in this video, we are going to solve this question from scratch without any guess of the function. And we will build up the concept step by step. And we are only going to apply the condition what we have at the hand. So the condition we have is f0 squared plus f dash 0 square is 85. And this is also one important condition I have. That the function fx, suppose you are taking any function fx, its codomain is given minus 2 to 2. It means the function maximum value is 2 and the minimum value is negative 2. It means if I take the function fx as a mod, that will always lie lesser than 2. Now, if you notice that if I take f mod of fx is lesser than 2, and I want to substitute 0 there at the place of x, so f0 mod will be also lesser than or equal to 2. I don't know what is the f0, but we know that for any x lying between this, not in the interval, any x coming from the real number, for whatever real number you take for x, the maximum value of the function could be 2 and the minimum value should be only negative 2. It means if you put 0 also, the f0 has the maximum value 2 only. So when you square it, that will give you 4. And so we are getting this f0 square has a maximum value 4. It means from this information, from here, I'm going to write what? f0 squared means rather f0 function square is equal to 85 minus f dash 0 square. It means I'm getting this value is lesser than 4, so this should be also lesser than 4. And so we can write f dash 0 square, this should be 4 here, I don't know why it's star came, 4. And this f 0 square can be written as greater than or equal to 81. It means I can infer that f0 mod is greater than 9. Now this information I have, this one information I have, and we are going to use it step by step in each of the options given to us. So let me take this thing aside. So these are the information we have, and now I have the first option, and the first option tells that there exists R and S belongs to a real number. where r is less than s such that f is 1, 1 and the open interval r to s. So f dash 0, because it actually saying that for any two number r and s there is in existence or not, and the function is 1, 1 they are claiming. So if the function is 1, 1, the function must be strictly increasing in that interval. So it is sufficient to notice or observe or prove that the function is whether increasing or not in such any open interval or not. If we can find such interval r to s in which the function is increasing, that is sufficient to tell that this statement is correct. So for that, what we are going to assume that, let's see here, not assume, is already I have. If we can notice that f dash 0 I can write greater than 9, and also f dash 0 lesser than minus 9 from this inequality. So let's assume this part only. Let's take this part. F dash 0 greater than 9 means what? If f dash 0 you are saying that greater than 9, it means I can claim that f dash 0 is greater than 0 only, because it's already greater than 9, so f dash 0 is positive. So if f dash 0 positive means at 0, at x equal to 0, fx is increasing. Now try to understand the scenario. Let's try to understand this entire concept by using the definition of increasing function at a single point. When a function is increasing at a single point, what is the claim or what is the definition? Suppose I have this point 0 here, and at 0 when you are saying that the function is increasing, it means if the function is increasing in a very small interval from a to b, if in this interval the function is increasing and in this interval 0 is lying, then we say the function is also increasing at 0. It means I must say fx is increasing at 0 only if there exists an interval a to b such that 0 belongs to a to b and in a to b f is increasing. So you are already saying that this f0 is increasing. It means there is an interval a to b in which the function was increasing. That's why by the definition we can say that yes, we have such values of r and s belongs to real number and r less than s in which the function can be 1, 1, and it comes from this increasing criteria, increasing definition. So this statement is absolutely correct. Let's go back to the statement B, not back. Let's go forward to the statement B. The statement B tells that there exists x naught belongs to -4 to 0 such that f dash x naught modulus is lesser than equal to 1. So x naught belongs to -4 to 0 and I have f dash x naught magnitude is lesser than 1. So this is the condition I have. There is such x naught existing in between -4 and 0. So whenever we see this kind of interval and they are asking the derivative at certain point between the interval, it reminds us the Lagrange's mean value theorem. So let's apply that Lagrange's mean value theorem between -4 and 0. So I'm claiming that I have such x naught, f dash x naught, between the -4 and 0, so that I have f0 minus f of -4 divided by 0 minus -4. And since I have to consider the magnitude of this quantity, I'm taking this magnitude both sides. In this way, what will happen to the right hand side is the f0 minus f of -4 mod, and this 0 minus -4 I can take it out. So now I have the difference of f0 and f of minus 4. And you notice that the f0 is lying between minus 2 and 2. For any x, fx is lying between negative 2 and 2. And f negative 4 is also lying between negative 2 and 2. So you take the difference and take the magnitude of the difference, means absolute difference. If you take that, the maximum value, or we can say directly like this, f0 minus f of minus 4, magnitude will be always lesser than 4. And of course the magnitude is greater than 0. It means when you're dividing this by 4, automatically this f dash x naught magnitude is coming to be lesser than or equal to 1. And so we have proved that f dash x naught is lesser than or equal to 1. And so this statement is also correct. And this is coming from Lagrange's mean value theorem. Let's move forward for option number C. And option number C tells the limit x tends to infinity fx is equal to 1. Limit x tends to infinity fx is equal to 1 is not the correct statement. Why? Because I have the function value lying between minus 2 and 2, and there is no such indication that the function has a limiting value somewhere, at very far or very near. So minus 2 to 2 function can take any value. And so there is no such kind of guaranteed statement that the fx will give you the value 1 when x approaches infinity. So this we can ignore. This is not a correct statement. The option C we can also disprove by just taking any function which is a periodic function. As I told in the beginning, that many examples or many solutions they have given by taking the function fx as a sin x function by some other adjustment by to take this entire value as 85. So if I take any trigonometric function, a periodic function, the limit x tends to infinity cannot be 1 because it's oscillating and it can be anything. So we can disprove by this logic also. Now we go to the option number D. So option number D is they're asking that there exists, let me just copy this option down. So in this option what they're asking that there exists alpha belongs to negative 4 to 4 such that f alpha plus f double dash alpha is equal to 0 provided f dash alpha not equal to 0. So I have this situation. You notice that f0 they have given f0 squared plus f dash 0 squared is equal to 85. Now by just observing this function structure, we can assume a new function in terms of fx and f dash x. How we can assume? Let's say hx I have as fx squared plus f dash x squared, and I'm claiming that h0 is 85. Not claiming means I'm assuming actually. Now the idea is that we can take this derivative and notice this structure will be there. How? We differentiate it, so we get 2fx f dash x, and here we get twice of f dash x into f double dash x. From there we can take twice of f dash x common, and here we get fx plus f double dash x. Now the idea is that how it can be 0 if f dash alpha not equal to 0. Now you notice that this is inviting to understand this concept or implement this concept that hx function is attaining either maxima or minima somewhere between negative 4 and 4. Then only that at that value, that let's say alpha is the point where the function hx is attaining its either minima or maxima, it means at that point only the function derivative, the h dash alpha, can be 0. And if h dash alpha is 0, of course f dash alpha is not 0, so automatically the f alpha plus f double dash alpha becomes 0. So we have to just understand whether this hx is attaining either maximum or minimum somewhere between -4 and 4 or not. So for that, what we do, let's try. This alpha we have already actually seen from the part B perhaps. We can notice here from part B what we have assumed, that f dash, not assumed, sorry, we have proved that f dash x naught mod is lesser than 1. So from B we have proved that f dash x naught mod is lesser than 1. Now if I have this situation, and let's say I am taking this square of it, and why I'm taking, you will understand in a minute. If I square it, I will also get f dash x naught square is lesser than 1. Now notice, if I want to find the hx value at x naught, and that x naught lies between -4 and 0, for the convenience I've taken here. So what will happen in this situation? You notice that let's say hx naught I'm taking. So hx naught will give you f x naught squared plus f dash x naught squared. This quantity is always lesser than 1. We have already proved here. And this quantity is always lesser than, let me just erase it. This quantity is always lesser than 4. How it is 4? Because we have already established this thing that fx naught is mod is always lesser than 2. And so fx naught actually, it is actually fx. Here you see that for any function, for any x, sorry, the function has a maximum value 2 only. So x naught is also in the same interval, so I can take that fx naught mod square is lesser than 4. It guarantees that hx naught for any such x naught is lesser than or equal to 5. So this x naught is lying between -4 and 0, for which hx naught is lesser than 5. Now notice one thing. The h0 is 85, we have already taken, and it is function is continuous and differentiable. So between -4 and 0, let's say this is -4 here, this is 0 here. At 0 it is attaining 85, and at -4 to 0 there is some number x naught at which the value is lesser than or equal to 5. So let's say this value is somewhere lesser than or equal to 5. This is 5, by the way. So it has to increase and attain its 85, the value 85 somewhere here. Now from 0 to 4 we can apply the similar Lagrange's mean value theorem. So let's say I have x naught belongs to 0 to 4, and again I'm saying that f dash x naught, not x naught, x1 rather, x1 bit belongs to 0 to 4, and f dash x1 I can write f of 4 minus f of 0 divided by 4 and take the magnitude again. And you can again see that f4 minus f0 will give you the difference, absolute value is lesser than or equal to 4, and that's why this will give you again f dash x1 mod is lesser than 1. Therefore f dash x1 square is also lesser than 1, and by the same logic I can say that the hx1 is also lesser than or equal to 5. So what is happening here between 0 and 4, that after is attaining the 85, the value 85 at 0, is not necessarily that 85 is the maximum value of the function, but after attaining 85 at 0, it has to attain this again some value which is lesser than 5 between 0 and 4. Let's say this is x1 here. So it has to come down to attain this value there. And in this process, when it is starting from x0 and going to x1, in this entire process between -4 and 0, it will attain its only maxima. It will attain its maxima somewhere, maybe it is either below 0 or maybe either here, or again it will take its 85 and come down, or it can be anywhere. But you can understand that in this process, the hx is attaining its maximum value somewhere, and that somewhere value I can assume at alpha. So there exists some alpha between -4 and 4 where h dash alpha is going to be 0. And so if h dash alpha is 0, it means f dash alpha times f alpha plus f double dash alpha is going to be 0. Provided f dash alpha not equal to 0, I can say that f alpha plus f double dash alpha is certainly to be 0. And so we have such alpha with this logic, and so the answer is option D is also correct. So that's all for today's video in JEE Advanced discussion series, that TWPW, it means the why behind what. See you in the next video with some other good advanced questions. Till then, stay math active.